Okay, so now let's go to electromagnetic waves proper in the next phase. This lecture 9B1 will do EM waves in free space. I had shared this plan for us for waves, and we have done the introduction to one-dimensional waves. Now in this lecture, I'll cover this shaded portion. That is how we obtain EM waves from Maxwell's equations and monochromatic waves in vacuum, okay, in this lecture. Maxwell's equations in vacuum. By vacuum or free space, I mean that there is no charge and there is no current. Where is that space? Okay, in normal air, in the planetary sphere, the light coming from sun to earth, we are all charge free and current free regions. Okay, so that is what we're talking about. What does that really mean? That really mean is there are no charges, and then in vacuum rho is equal to 0. In Maxwell's equations now we have done quite carefully, and J is equal to 0. All right. So in rho is equal to 0 and J is equal to 0, we can rewrite the standard Maxwell's equations uh, setting these two to be 0. Let's do that. So now instead of rho by epsilon, divergence of E is 0. There is no source for actual E electrostatically. Then this is anyway remains. Okay, there is del cross E minus del B by del T. This is always true. Divergence of B is 0. And in Maxwell's Ampere law, the J term, J is missing, mu naught J, because that has been set to 0. Now, this is for free space. This is a set of Maxwell's equations. That's what I meant by free space or vacuum. Now, what are these? These are really a set of coupled first order partial differential equations for E and B. First order, because there is only one differentiation in space and one differentiation in time, but they're coupled. Equation in B involves E, and equation in E involves B. So they're coupled, and all four need to be satisfied, of course. Okay, so then it's only a one line derivation for all the effort that we have put in. All right, so let's say what do? We take take this one and then take its curl, del cross C. And this we have done many times. We can now expand this. Divergence, uh, this is the gradient of the divergence of E minus del square E, and that should be nothing but minus uh, del cross minus del B by del T. Just have taken uh, the curl on both sides, del cross on both sides. Now we know this. This is the equation. So there is no source charge, and hence the first term is 0. All right. And now this one I can now uh, write down. So del by del T, del cross B, but del cross B is here, the fourth one. So I replace del cross B by mu naught epsilon naught del E by del T. And that is del by del T of this. So that is minus mu naught epsilon del square E by del T square. So similarly, I can take now this Maxwell's equation and put curl on both sides. Okay, so del cross B, then the gradient of divergence of B, but we know divergence of B is 0 always. Use that. So minus del square B is curl of minus mu naught epsilon d del B by del T. Now what is that? Del B by del T will come from here. So you can see the symmetry, right? So del B by del T will be, we can put in terms of del cross E, all right? And hence it will be del cross B by del T square, all right? So now you can see that these are decoupled equations. So what has survived is del square E and its terms of second order in time for E, and del square B, what survives is second order in B. So by doing this, okay, we have decoupled first order differential equations. So this was a first order equation. In decoupling, we pay the price for making it a second order differential equation. Okay, and so uh, let's write it down. The first one becomes then del square E mu naught epsilon del square E by del T square, and the second one of course becomes exactly similarly del square B mu naught epsilon del square B by del T square. Okay. And you can see the crucial role that this minus has played in being able to do this. Okay, the Lenge's law. So, and we get exactly mirroring the two equations. So you can see that after all that effort that we have put in learning Maxwell's equations and all the vector algebra, we is the derivation of the wave equation from Maxwell's equation is just one line each effort. All right, it's important. I hope this is something that you will remember even in your dream if you have done this course well. This is what we have been trying to arrive at for so long. So this is a decoupled second order differential equation for E and B. So now let's look at a little bit more. So that is so what we have gotten is a wave equation. Let's show that, and that gives us to light. Okay. So del square E. I'm just repeating this what we have gotten. Del square E. Okay, and of course del square B mu naught epsilon del square B by del T square. In free space, each of these Cartesian components, Ex, Ey, Ez, Bx, By, Bz, satisfies this three-dimensional wave equation like this. So Ex, Ey, Ez, so they will all satisfy this equation. Okay, and hence we can, and this is now um, mirroring. You see, this was our one-dimensional wave equation. So only thing in three dimension, it does become a del square. This was del square f by del z square. And then what is this v square? Now we can relate what is this v square. That is mu naught epsilon naught. 1 by v square is mu naught. Okay, so this was 1D equation. So that is Maxwell's equations now are implies that the empty space supports the propagation of electromagnetic waves traveling at speed. And what is the speed? Of course, this is v. Mu naught epsilon naught is 1 by v square. So v is mu naught epsilon naught. And we have already fixed this value. These are constants according to our development. So this is really the speed of light. So we have been able to obtain in free space E and B, which will support each other to travel at speed c. There is no source, no rho, no j, and yet E is creating B, B is creating E, and they keep on going. And that is how light travels in free space with speed, which is given exactly by mu naught epsilon. This was really astounding achievement at the time when it was achieved, because you remember the is the phenomena which associated with epsilon was associated with the attraction, let's say, of a comb on a charged on a paper. You comb and then it attracts, and a magnet attracting a piece of iron. That's where mu naught was involved. The two kind of phenomena. And astoundingly, these two phenomena are related to actual light traveling from stars or end of the universe to us at speed c with the same two constants that are involved in these two experiments. That was, I think one must, we are so familiar it now that we know almost on our fingertips this result. But you must appreciate that when it was first achieved, the kind of integration of different phenomena and then taking from magnets to electrostatics to electrodynamics to actual light. Okay, that was the course that the Maxwell's equation has taken for us to arrive at this result. So what I want you to notice is the crucial role played by the displacement current term in the Maxwell ampere. Now, so mu naught epsilon naught del E by del T, epsilon del E by del T, that term, okay, was missing earlier. Once you put that in, then the wave equation just becomes as simple. It just comes out of it. So his Maxwell's fixing of the Ampere's law was extremely crucial for obtaining the light waves out of Maxwell's equations. So we said we'll worry about sinusoidal, okay, and then we call it monochromatic plane waves. The fields are uniform over, look at this diagram. The fields are uniform over, okay, so this is E, and then, okay, so this is the propagation direction, okay, and uh, perpendicular to the direction there would be plane, and that is why they're called plane waves, okay. And why monochromatic? Because monochromatic means that these are single frequency, one color. Chrome is color and mono is one. Okay, so monochromatic wave. So we are going to deal with most of the time the monochromatic waves of single wavelength, okay, and single frequency uh, in a certain going in a certain direction. So if you can see that if I take one plane, then the E is there, and after some time I take the next plane. So over this plane, this is the E is constant, and then it can be changing as it progresses over the, and that is why it tends to a monochromatic wave is like a plane wave, as if the planes of constant E is traveling. Of course, E is changing, but at any point of time over one plane, it is constant. Okay. So E, let's look at EZT. Okay. Is E naught I kz minus omega t. You remember this tilde here, we have made it complex. So that's why I don't have delta here. So it is absorbed into the amplitude. All right. So this is going in the direction of plus z, kz. K is 2 pi by lambda, and of course omega is equal to ck. So bzt is also exactly, so b is amplitude and kz minus omega t. And how omega and k are related? Omega is equal to ck. Right. So this is a complete description of a monochromatic plane wave, okay, with a single frequency and single wavelength. So E naught and B naught are the complex amplitudes, okay, and physical fields are of course the real part of it, okay. But I want to show, this was already on our screen. I want to show that if it is traveling in this particular case of zone Z, then there is no component of this amplitude in the Z direction. Where does that come from? Okay, that comes from because del dot E is equal to 0 and del dot B is equal to 0. So we have gotten by the curl of the two of them, but we have to also impose this to the other two conditions. The fourth one doesn't give us much, but this is equal to 0. And this ensures that the Z component of B naught, E naught are 0. Okay, and this is the condition that makes that the electromagnetic waves are transverse. Okay, that is, there is no component of the field in the direction of propagation of the light, no components along direction of propagation. That is why they're transverse waves. Okay, now if I say del cross C minus del B by del T, then that gives me a new condition K. I'm just, okay, the Y component of E tilde, E naught tilde complex, I keep it complex now, and so this is from del cross E, okay, and del B by del T will give my omega, this is B naught of X. So minus K, okay, here the E naught. So if I take del cross E, okay, then from del cross E by I get K here, okay, and E naught Y minus K E naught Y. And if I take del B by del T, okay, then I get omega B naught X. Okay, so these two must be related. And hence, I get this condition that the two amplitudes of these two, in a monochromatic wave, the two amplitudes are related. So this is the Z is the direction in which it is propagated. So this is the propagation direction cross the E naught, the full E naught, that gives you B naught. So B naught and E naught in a monochromatic wave are related uh, as this. Okay, and similarly I can get my x and y, so these both components I can obtain, and from there I have generalized this. From here I can take now that the EB are in, what is important that we get, that EB are in phase and are mutually perpendicular, because B naught is, of course we can see that, so B naught and E naught are mutually perpendicular and they are in phase. When E is having going through maximum in a perpendicular direction, B is also going through a maximum in its own direction. Okay, they are perpendicular, and each one is in phase, but in two different independent perpendicular directions. So EB are in phase and mutually perpendicular. So, and if you want to just calculate the magnitude, of course, B naught K by omega E naught, and K by omega is not nothing but 1 by C. So B naught is E naught by C. Okay. So E naught, if you know the electric field value, then dividing it by C is B naught. So typically that's why actual B naught value is quite small, because it gets divided by this 3 into 10 to the power 8 meters per second. Okay, that is B naught. You will see that while working out our problems on lasers, we'll ask what is the magnitude of E naught and B naught in a laser light, for example. So going over it again, this is what will help you solve problems also. So monochromatic plane waves, you can write down Ez, Bz. The dispersion relationship is linear, omega is equal to Ck. E naught, B naught are complex amplitudes, and the fact that divergence of E and divergence B is zero gives you the result that electromagnetic waves are transverse. If you use del cross E, you get the space part, and that gives you minus k E naught y, and the time derivative part will give you omega b naught x for both. Okay, and that we generalize to the amplitudes of in a monochromatic wave are related to in this vectorial form. Okay, so you can see they are vectors. So while writing answers, you have to be very careful. You have to vectors. If it is complex, tilde, both of them must be there. Okay, so and if you don't write the vector, it can be a problem. Okay, many of our graders have complained that you don't put um, vector signs on vector quantities. Okay, so now let's go ahead and look at let's say one example to be able to see. Suppose B points in X direction. So there will be many problems in both in the exam and in the home assignment, in which there will be a word description of the electric field, and you have to write it down and obtain, if E is given, get B, if B is given, get E, or both are described in some form, and then obtain the mathematical form of the E and B for plane monochromatic waves. Okay, so in this case, it is given that B is pointing in X direction, which means the wave is traveling in X direction, and we know that E and B are in phase and mutually perpendicular. That's enough now to be able to, if it's in free space, and we'll be able to write it down. So let's look at how it is going. So suppose, so B is points in uh, B is the so B is pointing Z, is actually traveling in Z direction. B is pointing in Z direction. Okay, and monochromatic. So this is a mistake here. This B points in Z direction for a monochromatic wave traveling in X direction. B cannot point in X direction if it is traveling in X direction. So B is pointing in Z direction, as I have shown here, and then E would be pointing in Y direction. So this red is the way it is. So it is transverse because it's perpendicular. So this is, so it keeps peaks and then goes through and then goes through and then. And in the perpendicular direction, in the Z direction, B is traveling, and they are in phase. So when this is a maximum, B also is going through a maximum. When E is going through minimum, B is also going through a minimum. That a part of the results we have already obtained. All right. And of course, the speed is C and is K. Please, I will correct it. This is a typo. This must be Z direction. So this is going in k direction. So this picture, of course, one has in mind. I've specifically taken it in x direction because I have been showing everything in z direction. So ext, once I know that, then I can write down. So this is kx minus omega t, and e is pointing in y direction. Okay. So and e naught is complex. This is a complex. This is a vector, and vectors now the direction is taken by y, and this is the complex amplitude. And so b vector complex, and that is of course e by c, 1 by c, but pointing in the z direction. So this was pointing in y direction. This is same as e but divided by c but pointing in z direction. That's why how I have written it down. When you need to get used to writing from a word or visualizing a plane monochromatic wave in free space. So and so this is the complex, but I can get the real one. So ext, that's the real part of this. So this is y hat, okay, and then this is just the magnitude, the amplitude, and this is the cos of kx minus omega t. So this was complex. Now since I have now taken the real part, the delta can come in. That is fixed by, this is a phase constant. I have to write it down. So b is of course in the z hat direction, 1 by c, and with exactly the same phase factor as here, with the same phase constant because they're in phase. All right. So let's look at the generalized form. This I've given you some example, but general form of monochromatic wave. So I will introduce the most important, the propagation wave vector and the polarization vector in describing and writing down E and B. All right. In a So first thing to note that in general, if the direction of propagation is k hat, okay, in the direction of k it is moving, then nk dot, so n is the will associate with the polarization vector, that is oscillations happening, and we associate with the electric field by convention. The polarization direction is given by electric field, so which means n hat is the direction in which electric field is propagating, and electric field is oscillating, and the wave is propagating in the k direction. Okay, so nk dot is 0. So k is the wave vector. We'll call this the wave vector. This 2 pi by lambda with a direction, progression direction. Okay, the magnitude is 2 pi by lambda, but the direction is this way. It is going at a speed c, and but this I like to generalize. This was for a special case. So E, then I say that, all right, this is E as a function anytime, any space R, T. So E naught is the amplitude, the complex amplitude, okay, which also includes any delta that is there. And it is vibrating in the N hat, okay, in the N direction. And that is the, so this is called the propagation wave vector, K. Okay, now we used to write kz, kx, and so on. So we can generalize to k dot r is the, so r is, this is in terms of r. I'm generalizing it, minus omega t, and n is the direction in which it is, and that is the polarization vector, unit vector, which will tell you the direction in which E is oscillating. All right. So if I want that, then I can write down BRT, of course, of this 1 by C, K dot R minus omega T. But now it is perpendicular to both the E and to the propagation direction. Propagation direction is K hat. So K cross N. And this is the order, of course, matters, right? So it cannot be N cross K because it will make, then it will make it minus. So K cross N. So if I know E, then I can write down B in generalized form here. This is vector and complex. This is complex amplitude. Vector is given by K cross N. And this is K dot R. Let's picturize in, suppose this is traveling, this is the wave front, okay, the planar wave front, and I want it at position R, then I'm taking R dot K, K dot R in the direction, okay, of K dot R. R I'm taking in the direction of the propagation, that is this quantity. All right. So K dot R, and is traveling in k direction. So I can write down then in general then B complex complex and vector 1 by C k hat here is not z hat, okay, k in the direction of propagation of the wave vector cross E 1 by C. So we need to remember this to be able to write down to also do problems, okay. um, so and then I can, if once I know this, I can write down the actual E, the real E in terms of E naught and N hat, okay, and BRT now 1 by C cos k dot R minus omega t now k cross N hat. This is the real one. Simple, but one has to get used to this. Now, what is the energy and momentum in the EM waves? Waves also carry energy and momentum, and we have already all done that, okay, quite a bit. So, U, energy density, we have already seen is half epsilon naught E square plus B square mu naught. And hence, in case of monochromatic plane wave, okay, B square is E square by C square, okay. So, or as we said, B is, we saw that E by C, so epsilon naught mu naught by E square. Okay, and hence you can see that the electric and the magnetic contributions are equal. Okay, so this is, if you take B square and epsilon naught F square, mu naught cancels. That is also half epsilon naught E square. So electric component and magnetic component to energy are equal. They're symmetric, even energy wise. So the traveling wave carries energy with it, and so we know how to compute the energy flux, 1 by mu naught E cross B. So for a monochromatic wave we can work that out, okay, because we know E and B. uh, so let's say in the plane wave traveling in the z direction, then I simply put that in. So z, so this is nothing, C epsilon naught E square cos square. Okay, so this is U. So S E cross B. So you see U in the z hat. Okay, so this is the energy flux in the monochromatic wave. Is a cos square term, right? So this is U times the velocity of the wave. Okay, and that is that justified? That you can see. Suppose an area. This is an area A, and it's traveling in C direction. And what is the length of this? This is C delta T. All right. So um, so energy per unit time per unit area transported is UC, okay, in the direction of travel. Okay, U is this and UC is the energy. So that's, so now let's look at uh, the density. This was the energy. So you know momentum density. We have already calculated in the last lecture. So this is G, C S by C square. Okay, this was epsilon naught E cross B, and that gives you G 1 by C square of the related to the Poynting vector. So that's the momentum density. So if it is momentum density, then I already have S, okay, the Poynting vector. So I can calculate, and that will be 1 by C uz, and hence for for light waves, okay. So this is, we can calculate, okay. This is U by C. So momentum is U by C. The energy is UC. All right. For light waves, the wavelength is of the order of 4,000 to 7,000. So I'm taking the middle. So let's say 5 angstrom, 4,000 angstrom to 5,000 angstrom, or 400 nanometers to 500 nanometers. So of the order of 10 to the power minus 7 meters. Okay, and what is the time period in light wave? Okay, that, and this is of the order of 10 to the power minus 15 seconds. And normally this is too fast and too short a distance for us to worry about as a function of space and time period within the one wavelength or one time period. So when you are looking at transport of energy or momentum, we normally, because of that, look at the average over many cycles. Okay, so we are interested in energy average over many cycles because it's too fast and the distances wavelengths are too short. Okay, and hence we calculate this angular, this represents the time average. Okay, so if you take time average, then it is simply half epsilon naught E square. Why? If you actually do 0 to uh, over one period of time, over one cycle cos square, this will give you half. Okay, so similarly, I can work out the time average of the Poynting vector. That will be half c epsilon naught E square. It's a vector, so it's giving in the z direction. It's in the direction of the propagation. Okay, and it's important, and it's carrying momentum. Yes. Okay, 1 by 2 c epsilon t square is carrying momentum, average momentum in the time averaged momentum in the direction of propagation. Okay, so what is important is for light intensity. Normally, when we associate light, lower light intensity. So, in terms of these parameters, what is light intensity? Is nothing but the time averaged Poynting vector is light intensity. Okay, so when we say a particular laser is 5 milliwatts, okay, what I mean is this the time average Poynting vector is half c epsilon naught E square z. So if you know intensity, you can immediately calculate the E amplitude, maximum E in that laser light, or whichever light, if it is monochromatic. Typically lasers have monochromatic, and hence it's able to immediately able to compute the magnitude of E and magnitude of B, and so on and so forth. But what is important to remember, that what is the definition of intensity is the time averaged of the Poynting vector, because that is the energy flux that the beam is carrying. There's also the idea of the radiation pressure, because it's carrying momentum. Since it's carrying momentum, when it gets absorbed on a surface, it delivers that momentum. Okay, so that moment delivery of the momentum would mean that it is delivering some pressure, and that's called radiation pressure. And so if light falls on an absorbing surface, okay, then I know that in time delta t, the momentum transferred is del p, and that is just the momentum density, average momentum density into area, and over the length c delta t. Okay, or so that is the total momentum that is actually transferring, and hence the pressure I can calculate as 1 by a del p by del t, and that is nothing but half epsilon e square, and that's nothing but intensity by the speed of light. All right, so we have so radiation pressure, radiation intensity, so energy, Poynting vector, the momentum density, giving rise to average energy that it is carrying, average Poynting energy that it delivers, and average momentum it carries, what is light intensity, and radiation pressure. We can note, suppose it is a perfectly reflecting surface, okay, then it goes and hits uh, for a perfectly, then it comes back. So the amount of radiation pressure would be twice, okay, if it is a perfectly reflecting surface. So I'll stop here. In the next time, we'll take up EM waves in a dielectric and take it forward from there. Uh, Thank you.